Hello everybody. In this week we are discussing counter. In the last class we had seen asynchronous counter, we had seen up counter, we had seen down counter, we had seen up and down counter put into one particular circuit, and also we looked at one particular IC. Today's class we shall look at decoding logic, what it is and how it is useful in counter design context, and also we shall discuss synchronous counter, up counter, down counter and up down counter. Decoding logic, why decoding a counter state is important. So, for example, we consider the mod 8 up counter, asynchronous up counter that we had taken up in the previous class. Okay. So, the counter has got three flip flops, JK flip flops. Each one of the input is having 1 and 1. That means, whenever the clock trigger comes to its input, it toggles. Okay. And so, the counting state, as we had seen before in the last class, moves from 0 0, sorry, this is the output 0 0 0 to 0 0 1, then 0 1 0, then 0 1 1, then 1 0 0, then 1 0 1, 1 1 0, 1 1 1, and again it comes back to 0 0 0 and it continues. This we have already seen in the last class, we discussed this. Okay. Now, so this is happening internally. If we look at all the three inputs, we can understand that a counting of a specific number of clock or the trigger has happened. Okay. But to the external world, if we want to know that a count of 7 has taken place, do we need to sample all three of them and figure it out, or we can make a logic, an output, a separate output available which will go high whenever the count of 7 takes place. Okay. So, that we do not need an additional thing where we need to look at all the three values and from that infer whether a count of 7 has taken place or not, or count of 5 has taken place or some such thing. So, in this example we are showing that a count of 7 has taken place that can be understood by having a 3 input AND gate over here out in where A, B, C are connected in this manner, and when all of these A, B, C are high, as is the case over here in 7th after at the 7th point. Okay. So, 7th clock cycle, if we consider this as 0th, okay, then the output will go high for 1 clock period. Is it clear? Right. So, this output is 1, that means 7 clock edges starting from 0 has taken place. 1, 2, 3, okay, 1, 2, 3, 4, 5, 6 and 7. 7 clocking, 7 triggering has happened. Is it clear? So, this will again go high when another 7 occurs, right. So, this is the utility of having a decoding circuit by which we can figure out whether that particular count has taken place or not. Okay. Now, if we extend it, so instead of say 7, if we are interested in decoding whether a count of 5 has taken place or not. Okay. So, what shall we do? So, we shall put a output gate where the input of which will be C is the MSB here, C is changing, okay, with a frequency which is less than that of A and that of B, right. So, when C is 1, okay, B is 0 and A is 1, right, that indicates that a count of 5 has taken place, that means 5 clock edges have come starting from 0. Is it okay? Right. So, similarly 0, 1, 2, 3, 4, 5, 6, 7 we have already seen. So, depending on our requirement, we can put this decoding logic at the output of the counter and accordingly this output will go high whenever the count value in the counter reaches that one, and it remains high for one clock period. Okay. So, in this example you can see since this 0 will go high here, again that is A bar, B bar, C bar, all of them are 1 at this point, and again when it comes over here, right, 1, this decoder output, okay, this logic gate output. So, C, B both are 0 and A is 1, right, C is 0, C is 0, B is 0 and A is 1. So, that is the occasion when it will go high. So, that is the case when this is happening, right, this is going high here and again going high here. So, after every 8 clock cycle it will happen. Similarly, for the other cases, is it clear, right. So, in the circuit, in this place instead of 3 input AND gate, we shall put one of this connection, right, and we can take wherever A bar is there, we have to take it from the inverted output instead of A, the way it has been shown here, right. Now, instead of say mod 8, if we had a mod 16 counter, right. So, to have a count of say in that case say 15 or 14 depending on that in the requirement. So, we would have required a 4 input logic gate. Okay. So, depending on the number of the count value with the mod 16, mod 32, whether it will be 4 input, 5 input, accordingly the number of input for the decoding circuit will increase. Now, we look at what happens, one specific issue related to glitch that we discussed, we introduced in the last class regarding discussion related to asynchronous counter. So, the effect of propagation delay. So, in the previous diagram we did not consider it, now we are considering it. So, this is the time, okay, this is the clock, and here it is A, here it is B, here it is C. Okay. And we had seen in the previous class, this is the clock edge, this one, this blue line you can see, and A is getting triggered, right, and after one propagation delay, A value is changing from 1 to 0, because it is toggling in every clock edge, negative edge of the clock, right. Now, B gets triggered from A, clock of B flip flop is actually fed by A, sorry, this one, okay. A bar I shall discuss little later, right. So, after the negative edge of the clock, so another propagation delay is required for B to change state, and B will toggle every time A changes from high to low, okay. Similarly, for C, so there are 3 propagation delays. So, this we have seen in the last class. So, this is the way ABC changes its value, right, and the propagation delays are cumulative, right. Now, consider that we are looking for a count of 6, okay. So, then the decoding logic required is C, B, A bar, right. So, A bar is the complemented output of flip flop A. So, it is changing whenever E is going high, it is going low and vice versa. So, that is what is there in A bar, okay, A bar waveform, right, and this will go high, right, when this is 0 and A is, sorry, this is 1, C is 1, B is 1 and A is 0, that is A bar is 1, okay. So, this is happening where? When it reaches the count of 6, okay. So, this is the case, C is 1, B is 1 and A is 0, so A bar is 1, okay. So, these 3 are 1 at that time, A bar, B and C, and the output will go high, right, that is what you see, okay, right. And of course, this AND gate there will be small propagation delay which has not been shown here, okay, which is less compared to this flip flop propagation delay, okay. So, but there will be small delay over here, okay. But the idea here is that the output will go high when these 3 are 1, 1 and A is 0, that is A bar is 1, right. Now, moving forward, after 1 1 0 there is 1 1 1 and after 1 1 1 there is a it should be 0, 0 and 0. This is the value that is expected, right. But because of the propagation delay, right, after 1, 1, 1, you can see for a small duration it still remaining at 1, okay. B is 1, but A has already changed from 1 to 0. So, for a small time, for the duration of the propagation delay, you have got 1, 1, 0. After that, B has changed, right, but A has already changed, but C has not yet changed. So, for a small time 1, 0, 0 is there, and after that only you are getting the 0, 0, 0, okay, right. Now, whenever this 1, 1, 0 is there, okay, so this logic decoder output will go high for a brief period, okay. So, this is the glitch that you can see, and if this output is feeding another counter or another say sequential logic circuit which is counting the number of trigger that is happening, number of changes happening here, right. So, it will get a wrong message that a count of 6 has taken place, again a count of 6 has taken place just after 1 clock cycle, which is wrong, right. So, this is something which is a problem with asynchronous circuit, and we need to think of getting around solving this problem, addressing this problem, right. So, one way to solve this problem, okay, is to associate the clock and increasing the number of input to the decoding gate by 1. So, there were 3 inputs, now you are making it 4 input. So, when you associate the clock, and of course, clock period is considered much larger, right, than this propagation delay, then what is happening over here? So, this is getting ANDed, right. So, this propagation delay is occurring when the clock is there in the low value, right. You can see this is the way the clock is changing. So, the change is initiated when clock is going from high to low, okay, it is negative base triggered. So, this is the time clock is remaining at low. When you are ending it with the clock, then this glitch goes away, okay. Of course, we are not considering clock to be so fast that this delay so much that delay is coming when the clock is again becoming high, right. So, that is ruled out, okay. So, propagation delay and the number of flip flops considered and the clock period are such that it is occurring, the glitch is occurring when the clock is low, okay. So, then the glitch can get removed, right. So, this is one way of handling this problem. Now, this brings us to the discussion on synchronous counter, okay. So, in the synchronous counter, this accumulated delay and resulting glitch, this aspect are not there, okay. So, in the synchronous counter, all the flip flops are getting triggered by the same clock, okay. Now, we see here in this case two arrangements, okay. So, this is one circuit, this is another circuit, I mean they are giving you, they will give you the same result, okay. So, in the first circuit, what you see is that each of the flip flop has got 1 and 1, 1 and 1, 1 and 1. So, all of them can toggle, right, all of them can toggle whenever they get the clock, right. And you can see this clock is fed here in to flip flop A, this clock is again fed here through a AND gate, we will come to that AND gate part little later, and this is also fed here. So, effectively the clock is being available to all the 3 flip flops, right, which will make it a synchronous counter, right. So, of course, there is no AND logic here. So, every clock trigger it toggles, a flip flop A toggles the way we expect it to be the case, the least significant bit part of it in a CBA configuration. So, A is toggling at every place, okay, 0 1 0 1 0 1. More about these boxes etc. I shall discuss later, okay, in this diagram, in this table, all right. Next, for flip flop B, clock has come, right, but clock has come up to this, but clock will go, is allowed to go to this place only when A is high because of the AND logic, right. So, only when A is high, right, B will get the clock for which it will trigger, it will toggle, okay. And when A is 0, like this case, when A is 0, initialized with 0, 0, 0, A is 0, clock has come here as well as here, but the clock has not advanced to this point, right, for which A has toggled, but B has not toggled. You can see A has toggled, but B has not toggled, okay. So, when A is 1, right, that means the next clock cycle, right, then this is 1 and the clock has come. So, according to the clock, at the negative edge of the clock it will toggle, so it has become 0, 1. So, then again A has become 0. So, when A becomes 0, right, so this clock is not available, it is coming up to the AND gate input, right. So, it will remain at the same value, input is, because in that clock cycle there is no toggling happening. So, this is remaining 1, 1, and this continues, that way it is 0, 0, 1, 1, 0, 0, 1, 1, again it will go become 0, 0. So, that is for flip flop B. And for flip flop C, what is happening? For flip flop C, clock again has come, right, but when A and B, any one of them is 0, right, this output is 0, and when both of them are 1, that is, it has reached 1, 1, right, it has reached 1, 1, then only the clock is allowed to come over here and trigger the flip flop C, okay, and this flip flop C is getting triggered and the output, its value changes from 0 to 1. Again it will change when both of them are 1 and value will change to 0, okay. So, the value 1, 1 or 1, it is made available in the previous clock trigger itself, right. So, that way this is not contributing to the delay, okay, in the way that one flip flop, this is not actually triggering, A output is not triggering, it is only the clock is triggering. A output is just ensuring that the clock is made available. So, that way it is behaving like a synchronous counter, okay. Now, let us look at the other circuit, okay. So, in this the clock is directly fed to each of the flip flop, right. The first flip flop is toggling at every instance, right, and next flip flop, when A is 0, the output will remain 0, 0, no change. When A is 1, right, like this case, when A is 1, right, then this will, both of them are 1, J and K, so it will toggle. So, the output will become from 0 it will go to 1, right. So, next clocking instance it is 0, right. So, it will get a 0 here, so no toggling, right. Again it will get a 1 over here, so that will make it change from 1 to 0 for B, and similarly it continues, right. And for flip flop C, what happens, right, this is when both A and B are 1, right, then J and K both of them are 1, as is the case over here, then only when the clock comes it triggers, okay, it toggles. So, it becomes 0 to 1. So, every clock instance it gets a trigger, but the value, if it is 0 it will not change, if it is 1 it will toggle, fine. So, this is the way these three flip flops behave, and resulting values for CBA are 0, 0, 0, 0, 0, 1, 2, 1, 1, 1 and then 0, 0, 0. So, what is it? It is a up counter and it is synchronous, okay, clear. And because of this, if we look at the timing diagram, what is happening in this case? So, this is your clock, right, this is the negative edge of the clock, A is changing at every clock the way you have seen. So, basically this becomes after one propagation delay it changes, right. So, it is moving like this, Okay. And what about B, right? So, B is changing again with the edge whenever A is 1, this is A is 1, then only B will change when the clock trigger comes. Okay. So, clock trigger has come, B has changed because A is 1, right? Clear? So, it will change after 1 propagation delay only. So, A has changed, the A value has taken from 0 to 1 after 1 propagation delay, 1 to 0 1 propagation delay, B has gone from 0 to 1 after 1 propagation delay, right. So, there is no accumulated delay from A to B like asynchronous, right. Again B will change when A is 1, then the clock is at the clock trigger it will change from 1 to 0 and so on and so forth. And what about C? C will change, we have seen, when both B and C are 1. So, this and this, when both of them are 1, right, at the clock trigger it changes, right, and it changes after 1 propagation delay only, right. So, this has become 0 to 1. Again it occurs in this place, when both of them are 1, it has gone from 1 to 0. So, that way you have got the timing diagram where the flip-flops are all changing at the same clock trigger and the values are available after 1 propagation delay, right. And because of which if we have got a decoding the way we were decoding a synchronous up counter, say 1 1 0, right, and in this case, so A bar is just following A, the complemented output. So, at this time this is 1 1 1, this 3 1, right. So, at that time this output will be 0. So, the propagation delay associated with this AND gate has not been shown in this diagram, but there will be small propagation delay as was the case for the last timing diagram, okay, and it will remain high for 1 clock period, right. So, this is the way it can, the count of 6 can be decoded, right. Now, let us look at synchronous down counter. Okay. Like we had asynchronous down counter following asynchronous up counter, now we have synchronous down counter, right. In asynchronous down counter, we remember that A bar was given as input, okay, and then B bar was given as input to the next flip flop, the clock and all, right. So, here we would be following the same logic, right. So, first we look at the sequence, okay, the down count sequence, then we can see what would be the corresponding circuit. So, down count sequence is, if we start from 0, then it goes to 7, we are talking about mod 8 counter only, right, but it can be extended to mod 16 and other values. So, 7, 6, 1 1 0, 5, 1 0 1, 4 1 0 0, 0 1 1, 0 1 0, 0 0 1, 0 0 0, again it is 1 1 1. So, this way it repeats, isn't it. So, that is your down count. Okay. So, the first, if we look at A is toggling at every clocking clock cycle, right, clock edge clock. So, this is how A is connected, both the inputs are 1, is fine, right. Now, when B is changing, you can see when this 0 black underline is there, whenever there is a 0, okay, with the clock trigger A has value 0, right, with the clock trigger, right, we see that it is changing, right, again A has 0, with the clock trigger it is changing, right. So, this is changing from 0 to 1, this is changing from 1 to 0, again 0 to 1 and so on and so forth, right. Now, to make change happen in a flip flop, we need 1 1 at the input, right, just in the toggle mode for a JK flip flop. So, for 0 it is changing. So, instead of 0 A, we will put, if we put A bar, that means that will make whenever A is 0, 1 1 fade as the input to J and K, and with the clock it will toggle. So, that is the way the connection has been made here, clear. So, similarly, for C to change, what we see that follow this brown underline, when both of B and A are 0, it is changing, again 0 0 it is changing, right, again 0 0 it is changing, right, and both of A and B 0 0 means A bar and B bar are 1. So, that way, right, we can take this A bar and B bar ANDed and put them together, and we can get a output, we can get a circuit like this. Okay. So, that will give you a synchronous down counter, right. And like what we discussed in the previous previous class, asynchronous up and down counter, instead of A, B, C, if you take output, if so possible, from A bar, B bar, C bar, the output will be just opposite. A, B, C, if it gives down count, A bar, B bar, C bar will be giving you up count. Okay. And similarly, in the previous case also for up counter design, if you take the output from the inverted terminal, complemented terminal, it will be giving you a down count. Okay. Now, we can move to synchronous up and down counter, right. So, again there can be two arrangement. So, in one arrangement, there are two clocks, one is count up. Okay. So, when we are giving the clock through this, then the countdown clock is 0. Okay. So, countdown clock is 0, this input is 0, right, whenever we are feeding clock here, right. So, this A is coming over here, it is the first circuit, first arrangement that we had seen in the discussion related to up counter, and its corresponding counterpart is coming here for the down counter, right. So, this is coming. So, basically then A ANDed with this clock is fed here, right, and this will be 0 because this is 0. Similarly, the A and B ANDed with the clock will come here, and this output will be 0, and so on, and it will continue. Okay, right. And if we have if we are looking for down count, then we want to feed the clock through A bar, B bar, A bar, B bar here, A bar, B bar, C bar over here, right. So, that is what we will do, and we will put this to be 0, and this is the clock that will be fed here, right. And in the other arrangement, again similar to these asynchronous up down counter, we can have a mode control input, right, when if it is 0, right. So, then this is 1 and this is 0, right. So, all these AND gates outputs will be 0 0 0, right, and then A is fed to JK input, and in this case A and B ANDed is fed to the JK input. Here this is your A, right. So, this is A, B, and of course, M bar is there with it, right, and this is your A, B is already there, A, B, C, and M bar is there, right. So, you can have a 3 input AND gate also, like the one that you had seen before in this case instead, right. Here we are only having in all the cases, because we are feeding the AND logic AND gate output of the previous stage. So, every case we have got a 2 input gate, but remember in this case there is a small accumulation of delay, right, because this delay gets accumulated. So, that issue may come up if you are clocking it too fast, right. So, that need to be taken care of. Okay. Otherwise, it is just only one propagation delay, but then too many if for a larger number of bit flip flop associated in the counter design, then the fan in could be an issue if we go for multi input AND gates. And this arrangement, there is only we are having 2 input AND gates, but the thing is that there is a accumulation of delay before clocking, of course, right, not after clocking, right. But so a flip flop has changed. So, after that the delayed value will make the appropriate clocking available to the next flip flop. Okay. So, that we need to take note of. And for m is equal to 1, we know that the down counter A bar, B bar, C bar, these are the one that will be fed here. Okay. So, this is how we can design a synchronous up down counter. So, with this we conclude. So, quickly a decoding gate connected to the outputs of a counter is activated only when a counter content is equal to a given state. For optimal use of a number of flip flops in counter design, n bit counter requires n input logic gate for decoding. Okay. So, for mod 8 we have seen that 3 input logic gate will be required for mod 16 4 input and so on and so forth. So, decoding gate strobed by clock can remove propagation delay related to glitch in asynchronous counter. In synchronous counter, every flip-flop is triggered simultaneously, which avoids accumulation of delay and possible glitch. Unlike asynchronous counter, additional logic gates are required in synchronous counter. So, in asynchronous counter, we have seen that output of one flip-flop is fed as clock to the next flip-flop. Here, we are putting some additional logic gates in the synchronous counter circuit. And design of synchronous up-down counter is analogous to asynchronous counterpart, where we are feeding for up count certain input and for down count certain other input, and the intermediate logic or the box is 2 to 1 multiplexer, the way it works. Okay? Thank you.